Hey everyone. So today we are going to be digging a little bit into transfer learning. So before we actually go and write a model, that'll be the next time, we want to learn how to train models, and honestly, for the most part, what you'll be doing in research is a lot of transfer learning. And so what exactly is transfer learning? So let's kind of break neural networks down a little bit into what they exactly do. So what we're going to be exploring today is transfer learning, right? And so transfer learning is something that's fundamentally unique to neural networks, and why I actually think it's so popular, why it's such an impressive algorithm that can do so many different things. So here's the idea, right? Here's the main idea. If you have a neural network, right, neural networks actually have two different things going on. There's feature extraction, plus classification or regression, but we're going to do classification for now. Right? There's both of these things happen end to end. So a way to think about this is today we're going to be looking at the AlexNet model, which was probably one of the earliest examples of convolutional neural networks. That word doesn't need to mean anything to you yet. We will dig into convolutions in the future. But it is a class of neural networks that's specifically for image processing. Right? And it does it via a mechanism known as the convolution, which again we'll look at later. So it does image processing, specifically image classification, right? It can take an image and tell you what it is. So what was the original way that people would do image classification before something like AlexNet, a neural network? Well, they would have to do feature extraction, right? So this part was done by humans, right? This is prior, so this is before neural networks, right? Before neural networks. A human would have to sit down and extract features from an image, and we'll look at what those features may look like in just a bit. So humans would extract some kind of set of features, from your image. Feature 1, feature 2, feature 3, whatever it may be. These features were then passed to a classification model. That could be a support vector machine, a random forest classifier, or really any classifier you can think of, right? Anything you want. So a human would extract features, and we'd pass it to a classification model. Now, this sounds all well and good, except for one thing. How do we know that these features here that a human has decided to extract is sufficient to express all the diversity in the images you want to classify? This might be simple in some cases. Let's say you only wanted to classify between, let's say we had images of happy faces, so you have a happy face, and sad faces, right? Sad faces. Well, what's the easiest way to classify between this? Well, what you'd have to do is write an algorithm, a feature extractor of some sort, that can look at your image and maybe extract the mouth, right? Extract the mouth, and then based on the contour of the mouth, if it's facing upwards or downwards, that tells us, is it happy or sad? So this would be a feature, the contour of the mouth. This feature would be provided to a classification model, which could then use that information to do the classification. Now, this is, again, a very reductive and simple example, but what if we scale it up a little bit more? What if we want to classify between dogs and cats, right? So if we talked about this briefly in the very first Intro to PyTorch video, but an image, right? If you have an image, really an image is a set of pixel values, right? Set of pixel values. So you have these pixels here. This would be a very, very tiny 3x3 image. So we have 9 pixel values here. And our model gets raw pixel values. Or in our case, if we're going to extract features, our feature extractor gets raw pixel values and needs to come up with kind of vectors or some numerical representation of this feature that we extracted from this image. And there's actually all sorts of feature extractors. If you've taken any kind of computer vision course, you might have heard of SIFT, which is like shift invariant features, and there's a large class of features that we could. There's like histogram based ones and so on and so forth. So there's a ton of features that we can extract from our image. These features will be basically a numerical representation, which is again passed to some support vector machine, some random forest, ... But again, the big idea is we need to extract stuff from our image that's numerically represented, and then these numerical representations, paired with some classification of what is it, is passed to a model to do our classification. As our images become more and more complicated, like dogs versus cats, or all of ImageNet, which has dogs, cats, bridges, and there's tons of types of dogs and there's tons of types of cats, and it's kind of complicated. There's no way that a human could sit down and come up with every single feature possible that would represent a large domain of images, if that makes sense, right? It would be almost infeasible for me to sit down and think of all the different things I can extract on an image that will cover a feature space large enough to represent a diverse set of images. So in that case, what neural networks do is, instead of manually extracting features and then passing it to a classifier, what if we do it end to end? We will have the neural network both extract features and do the classification at the exact same time, right? So this is why neural networks are super cool, because they can do all of this on their own. So let's quickly take a look, right, at an example here. So let me scroll down. Here's a picture of my cat, right? And so let's think about this a little bit. If we wanted to extract features that can classify this as a cat, well, what are the kinds of things that you want to do? Well, in an image, there's some features that are very generic, like lines and edges, maybe things like that. So maybe we would extract some of these lines, kind of like this. We'd have maybe the shape of the nose, kind of like this. Maybe the shape of the mouth is kind of like this, and we'll extract other features, right? So this is a very low level feature because it's representing lines in our image. There's other types of low level features we can do, like color information, right? What is the color here, right? Color. There's also high level features, right? Things that represent a cat. So cats typically will have ears kind of in this shape, right? That's a high level feature, something that's representing the cat. So let's kind of group this up. We have low level, right? This would be lines, edges, colors, contours, ... right? All these kind of low-level features, that's kind of in everything, right? Or maybe brightness, right? Hue, saturation, ... right? All sorts of stuff that are low-level features. And these are things that are representative in all images, right? All images have low-level features. But then we have high-level features, right? These are the features that represent the thing we actually want to classify. So in a cat, it could be the ears, the nose, shape of iris, ... right? The things that actually represent the cat. Like cats typically have eyes kind of in this shape, right? Eyes kind of in this shape. So a neural network, if we break it down now, right? A neural network, we pass in an image, so this is the image that we're passing in of our cat, and it's going to go through a bunch of layers of extraction. So in our initial example, from the very first one, we looked at linear layers, right? Linear layers. And regardless of what we're looking at, linear layers or what we'll look at later, convolution layers, they all do the same thing. But convolutions are the better choice for image processing. And again, we'll look at all of that later. Today's just to provide intuition. And all of these are connected to each other, right? These are all connected to each other. And then we have our classification layer, right? And this will predict, is it a dog or is it a cat, like the example we'll do today. So we have an image, we give it to a layer, and some processing happens here, some processing happens here, some processing happens here, here, so on and so forth. And obviously, because this is a neural network, there's going to be some non-linearity between these things. We talked about this, like the ReLU function or the sigmoid function, some activation function, right? So there's going to be some non-linearity. And the thing is that, interestingly enough, how neural networks end up working is early layers like this end up extracting low-level features. And then higher parts of a neural network end up extracting high-level features, right? So you can kind of think of it as a kind of an order of operations here, of going from lower level features to higher level features. This kind of makes sense because the model will accumulate or learn some type of low level features like edges and shapes and stuff like that. And once the model has learned to identify what is the edges and what are edges and what are shapes and what are colors and things like that, the high level features can then use these edges and stuff to identify, is this an eye? Is this an ear? What am I exactly, like, what is this the edge of, right? So you have a hierarchy, that's probably the better word. You have a hierarchy of features going from low level to high level is the intuition. And so what we can do is train a model to automatically extract these features and then use these extracted features to actually classify. So this is our feature extraction, and this is our classification. So there's kind of two parts going on here, just like this. Now, transfer learning is basically the idea of applying this, but reusing some parts of it. So here's the big idea. We talked about how neural networks require massive amounts of data, right? Massive amounts of data. We haven't trained on any big data sets yet because we just stuck to the easy MNIST example just for simplicity. But typically, neural networks need to be trained on at least a minimum of 1 million images, right? So the ImageNet dataset. So later we'll be reproducing things like ResNet, ImageNet. So we'll be reproducing ResNet and vision transformers on this ImageNet dataset. This has about 1.2 million images, right? 1.2 million images. And this was actually the original data set that AlexNet was trained on. This was kind of the ImageNet. There's a competition of who can get the best accuracy on this. There's 1.2 million images, and there's 1,000 classes. Now, of these, there's like a bunch of different types of dogs and a bunch of different types of cats, and there's bridges and birds and all sorts of stuff. There's all sorts of stuff kind of inside this thing. So what we have to do is say that this is the minimum number of images to kind of train a model from scratch, right? So we have this neural network, right? This is a neural network. And this neural network is composed of a feature extractor combined with a classifier, right? There's kind of two pieces here. And what we're going to do is, and this classifier in this case will have 1,000 outputs because there's 1,000 possibilities that it could be. So we can train our model to take in an image and predict the class. What is it? And as long as we have enough data and our model is sufficiently large, the model should be able to do this very well. And this is kind of great. The problem is this ImageNet dataset is a little bit useless to us, right? When we train neural networks or when we train models in general, we have something in mind, right? Something that we want to do. And typically what we want to do just doesn't have a ton of data lying around, right? A good example of this is, let's say you are a botanist, right? You're a botanist, and you have some pictures of leaves, right? You have some pictures of leaves, and you have this leaf here, and you might have a different leaf. I don't know how to draw leaves, obviously. Let's say this is a different leaf here. And so this is leaf 1, and leaf 2. And you want to create a app or maybe a program that can take a picture of a leaf and tell you what it is. What tree does it belong to, right? That's a pretty typical thing. Now, you, the botanist, may only have maybe 100 images or so, right? 100 images, maybe 50 of each, right? 50 of one, 50 of two. 100 images is not enough. It's not enough to train a neural network, right? We need millions, at least 1 million images to train a neural network like this. But most models are trained on significantly larger data, like 300 billion images or something like that. So this is a bit of a problem, right? How do we train a model to do this? Well, let's kind of go through our intuition. Our neural network has learned on the large data set, we've already trained it on a giant data set, how to extract low-level and high-level features. The only thing that's really different now is the class, right? Is the class. So these low and high-level features are actually generic, and we talked about this, right? Especially the low-level features. Every image, no matter what image you're looking at, has lines, edges, colors, contours, brightness, hue, saturation, so on and so forth. What our leafs may not have, or what our leafs don't have, is things like ears, nose, shape of iris, right? The high-level feature is representations of the data we're training on. The low-level features are representations of the data in general. So why not reuse the low-level features? Let's reuse it. So what we can do is, instead of training the model from scratch, right, let's first train the model on the 1.2 million images. And this is called this is known as a pre-trained model, right? It has already been pre-trained on a large amount of images. And then what we'll do is we can just go ahead and delete the classifier here, right? We'll leave the feature extractor intact, right? This has already been pre-trained, right? This is pre-trained, already pre-trained. So we can then delete the classifier. And now, instead of passing in the 1.2 million images, we're going to pass in images of our leaves instead. And we're going to create a new classifier that has two outputs for our either our leaf 1 or leaf 2. So this is the big idea, right? Again, as I just want to recap this because this is super important. We first train our model on a ton of data so it's capable of doing successful feature extraction. And if the model can predict which of the 1,000 classes is it from the 1.2 million images, then this model is successful at extracting nice feature representations from our image. Once the feature representation has been learned, what we want to do is, okay, I can do this 1,000 class task here from ImageNet, but that's kind of useless to us. I'm a botanist, and I want to be able to predict between these two leaves. So now I will just redo it. I'll continue training my model on my new data and just keep the feature extractor from before, the pre-trained feature extractor, and just swap out the classifier because I only have two outputs now rather than 1,000 from before. And this step here is typically known as fine-tuning, right? So pre-training and fine-tuning. So enough about that. Let's go ahead and do it. That's a little bit of a roundabout introduction, but should give you the intuition of what's going on. There we go. All right. So let's go ahead and implement it. So here's actually a really good picture, I think, that's very representative of what I'm trying to explain. Notice how so they I forgot exactly where I got this image, but you can just check the credits. That's fine. Notice how in these layers of representation, the first layer learns simple things like edges, maybe some shapes or colors, things like that. The second layer starts learning things about the face, right? Like noses, eyes, ears, stuff along those lines. And the third representation learns actually the face, like it's representing the faces themselves. So this is kind of that hierarchy of computation that I keep talking about, and that's why deep learning is really cool, because it has these stacks of operations. So I've went ahead and done my imports. Today, we will be using the predefined AlexNet model from PyTorch. We could obviously write our own. We will write our own next time, but today I just want to focus on really the thing that most people would be doing, grabbing a model that's already been trained to do one thing and fine-tune it to do something else. And today we'll be training it on the dogs versus cats images. If you have not taken a look at the Dataloader video from last time, I would actually recommend to just start at the beginning and work your way forward and go step at a time, because I will be kind of using stuff from before to do future tutorials. So all right, so let's go ahead. Yeah, so again, if you didn't check out the Dataloader, definitely watch the Dataloader video, because I'm not going to explain all of that again. So path to data, I think I put it in data dogs versus cats. Let's not list dir path to data, and I think I need to run the cell above real quick. There we go. I never imported OS, that's fine. import OS. And there you go. Yeah, dogs and cats folder, so no big deal. And we're just going to do our data set is equal to image folder. And it's going to be on the path to data. And that's it for now. Now, one thing that we talked about again in the data loader is that when we create a data loader or a PyTorch data set, we need to make sure that all of the images in this case are of the same size. So we're going to resize our images and normalize them, right? So let's go ahead and do that. Train transforms is equal to transforms.compose. And here we're going to do basically the list of transformations that we want. So we want to make sure every single image is 224 by 224. Why do I pick 224? It's because AlexNet, the model that we will be fine-tuning, expects images of size 224. So we're going to do transforms.resize 224 by 224. So no big deal. Then we're going to do some data augmentation. We're going to dig into this a little bit more in the future of the importance of this, but you can imagine that when you don't have large data sets, the model is likely to overfit, right? We talked about this. A model can just overfit or memorize the training data. So one way to deal with this is to give the model kind of a fake or simulated variety of data. So this means if you have a dog, if you horizontally flip the dog, if you just kind of, flip it over, it's still a dog, no matter what orientation you're looking at it in. So as long as it's a dog, then we can kind of provide the data random augmentations and stuff like that. And we'll dig into all of this more in the future. But for now, we're going to do transforms.random horizontal flip. And by default, p equals 0.5 here, meaning it's 50-50. Half the time it's going to be one orientation, half the time it'll flip to the other orientation. So no big deal there. Then we're going to do transforms.toTensor, right? We have to convert our image to an actual tensor, and then we have to normalize, right? So we have to do a normalizer. So normalizer. So if you don't know what normalization is, I do expect that you've seen machine learning a little bit before. A typical thing we do in machine learning is before we give our model some data, we will pre-normalize our data just so we're basically z-score standardizing our data. That's just a typical thing to do. It's good for the model. Models typically work well on kind of nice, normally distributed data. So we're going to go with that. So we're going to do our normalizer is going to be transforms.normalize, and we have to provide a mean and standard deviation. So if you remember, images are, especially color images, right? So I'm assuming we're working on color images here, is RGB, right? There's 3 channels, the red channel, green channel, and blue channel. And each channel is between 0 and 1. Technically, it's between 0 and 255, but we scale it to basically be between 0 and 1 by dividing by 255. So each channel has pixel values that are between 0 and 1. What we're going to do is, for each channel, R, G, and B, we take the mean, and we take the standard deviation, and just compute that for the whole data set, right? What is the mean of the R channel for all 1.2 million images of ImageNet? What is the standard deviation of the R channel for all 1.2 million images of ImageNet? And we repeat that for each channel, R, G, and B. If you're working on a custom data set that looks very different, we're working on dogs and cats, so it's pretty similar to the domain of our ImageNet data set. But if you're working on a custom data set, like maybe MRI images or something along those lines, it's best if you actually compute your own mean and standard deviation for this normalization process. So for now, right, we just need to normalize our data. So we just need to provide it the mean. So mean is equal to, and these are numbers that are very typical, right? So you can actually just look online and find them, and 0.485, 0.456, and 0.406. These are the means of the R, G, and B channels of our ImageNet dataset. And then the standard deviation is, again, 0.229, 0.224, and 0.225. And these are the standard deviations of the R, G, and B channels. Where did I get this? Someone had already pre-computed it for ImageNet, so we're just using it. right? Someone has already done this work for us to compute these coefficients for, or not coefficients, but these numbers for us. So we now have our normalizer. Spelled that wrong. So we now have our train transforms. If you take a look at it, right, it's a stack of every image. We're going to resize it, flip it randomly to give some variety, convert it to a tensor, and then normalize it. And this 2 tensor will ensure that it's between 0 and 1. When we normalize it, it'll be somewhere between -1 and 1 or something along those lines. So now that we have that, we just need to make sure that our data set uses these transforms. So we can do transform is equal to train transforms. And our data set will look like this, right? We have about 24,931 images, and we have, these are the transformations we'll be applying. If we do for sample in dataset, print sample, break, right? Here's one of those images, and notice it's an image and a class, right? So 0 in this case. So nothing crazy, right? This should feel mostly familiar to you if you had done the data loader already. So we actually, in the data loader tutorial, we wrote our own image dataset class, but PyTorch offers this image folder, which makes life very simple. So we're just going to go with that. Great. Now, next step is we need to load our model. So before, if you remember, we did class, we do AlexNet, and then module, ... right? This is kind of the process of writing a model. Today, we're not going to be writing a model. We'll again be writing the AlexNet model next time. We just want to load our model. So we're going to do model is equal to AlexNet. I think the N is actually uppercase. Oh, there we go. And model. So here is our model. What we have is a features. And in the features, we have all these convolutions. We have something called an adaptive average pooling right here. And then we have a classifier. Now, for today, I want you to treat all of this like a big black box model, right? I don't expect you to know what convolutions are, what max pools are, and what average pooling is. You should be familiar with ReLU, right? We've seen that before. And you should be familiar with linear layers. You should not be familiar with dropout. So we haven't talked about any of this yet, so don't worry about it, right? Just treat it like a black box model. The only things I want you to keep in mind, actually the only thing I want you to keep in mind, is this here is your feature extractor, and convolutions are powerful feature extractors for images, and we'll again see why later. And the other thing is, notice in the classifier 6, the very last output has 1,000 output features, right? 1,000, because this is meant to be trained on the ImageNet data. Now this AlexNet that we just picked out here, that we just loaded here, is not a pre-trained model. It is a randomly initialized model that's ready to be pre-trained. We just won't be, and you'll see why later. So we're going to do a couple of different things. So we have our model here, so no big deal there. Let's look at one thing. We need to be able to access. How do we access different parts of the model? So if we do model.features, right, that'll just be the features. That's just this part right here. If we do model.classifier, well, that's just going to be this portion right here. If we do model.classifier bracket 1, well, that's going to be in 9216 out 4096. So in 9216 out 4096. So we've accessed this linear layer here. And that's basically it, right? That's how we can access different portions of the model. So here, right, what is the output of the model? Like I said, right, this last layer in 4096 out 1000 is our output of the model. This is the actual classifier. And so the way you should think about this is in the case of MNIST, right, when you have 10 digits, this one should be 10. There should be 10 outputs. In the case of dogs versus cats, this needs to be 2. In the case of ImageNet, this needs to be 1000, right? So you just pick whatever your output class needs to be. And so we can go ahead and update the model, right? This model we cannot use yet. We need a model with just 2 outputs. So let's go ahead and swap that out. We can do model. Oh, there we go. Model.classifier. And what we're going to do is index 6, right? That's this linear layer here. and we're going to replace it with a nn.linear. Now, one thing to keep in mind, what we want to change is the output features. The input features have to stay the same, otherwise this won't work. Remember, in every linear layer, the output features of the previous layer has to be the input features to the next layer. So if we're outputting 4096 here, the next one has to input 4096. So we can't change that. So this one has to be 4096 for this part right here, 4096. But our output will be 2 because that's what we want. And so if we take a quick look at our model now, it's 4096 in, 2 out for our dogs and cats. So that should be pretty clear, right? That should be pretty clear about what's going on. And so now what we're going to do is create some random data. We're going to do rand data, be torch.randn, 16 by 3 by 224, 224. So what is this? This is a batch size of 16, so that's 16 images. Each image has 3 channels, and each channel is 224 by 224 because that is what AlexNet expects. And we can do model, rand data, and then look at the shape of it, and you can see it's 16 by 2. So for every single image, for the 16 of them, we have 2 outputs, right? Is it a dog or is it a cat? If it was again ImageNet, then this would be 1,000 outputs, so on and so forth. So now that we have this, now that our model is ready, we can go ahead and parse the model a little bit more, right? So one thing that we typically care about is how many parameters are in this model, right? How many learnable parameters are in the model? So we can do that. So we can do for model in named parameters, or for param, or let's see, name param in model.named parameters. We can first print out the name. We can print out the name, and let's just break here real quick. So the first, well, I guess we can print them all out, right? These are all the layers, and this should look exactly like what we had before, right? Feature 0, feature 2, or feature 0, and then, so that's feature 0, weight and bias, right? Because a linear layer has weights and a bias. Then we have, or I guess these are convolution layers, my bad, right? So a convolution layer has weights and biases. And then the next learnable layer is 3, conv2d here. So we can see features 3, then feature 6, feature 8, feature 10, and then we have all our classifier layers. So these are all the learnable stuff, all the learnable parameters in our model. So we can also look at param, print param, break. So these are the parameters in the first convolution layer, right? These are the learnable parameters in the first convolution layer. And if you do dot, I think we can do numl. Yeah. So this shows you we have 23,232 learnable parameters in just the first convolution layer. That's actually a lot, right? But we have 23,232 layers. So what we're going to do is we're going to create a thing up here called num params 0. And we're going to do num params plus equals numl, or number of elements. Then we can do num params. And we can see this model has, let's see, 1, 2, 3, 1, so 57 million parameters, right? This model has 57 million learnable parameters. Now that sounds like a lot. It's actually very small. Most models today will have close to easily 100 million, but honestly, significant models out there, especially those language models out there, have 1 billion or 5 billion or tens of billions or even, a couple 100 billion, right? So very large models, but today we'll be training a relatively small 57 million parameter model. Great, so now that we have that, right, that's just a quick check of how many learnable parameters are in the model. And just as a quick if name, I'm just doing the bias because it won't take up the whole thing. So there we go. Oh, or not name. If bias is in name, this is just so it's short. This is the case for all the learnable parameters. Remember, it's learnable because requires grad is true. Right, requires grad is true, which means these are gradient optimizable through either stochastic gradient descent or atom or anything else. So that should be kind of there. Great, so now let's go ahead and train our model, right? What we want to do is train our model from scratch on kind of these weights. So these weights are not pre-initialized. they are randomly initialized weights that are ready to be trained. So let's go ahead and do it. So this will be a slightly more in-depth training loop compared to last time. So I'm going to spend a little bit of time on this, but after this, we're going to kind of like, quickly go through the training loops for future videos. This is just to give you an idea of what's going on. So we're going to do CUDA if torch.cuda.isAvailable, right? Else CPU. So this is going to make sure, do we have a GPU or not, if CUDA is available. If you want to know how many GPUs and stuff like that you have, you can do NVIDIA SMI in your terminal or exclamation NVIDIA SMI in Jupyter, and you can see what resources you have, and we can see we have, these resources in this computer. So that's our GPU. If you have multiple GPUs like I do, then you can provide it which GPU do you want to use, and that you can do that by like CUDA 0 for the first GPU, CUDA 1 for the second GPU, so on and so forth. Otherwise, it'll just default for the first one. And so we can do print training on device, right? Training on CUDA. Good. And so our model was, again, AlexNet. We then took our model.classifier6 and swapped it out with an nn.linear 4096 to 2. And model is equal to model.to device, right? We have to make sure our model is sitting on the GPU that we want to train on. Otherwise, we'll get that CUDA error like we saw in the very first video. And so now we have to decide some model training stuff. How many epochs do we want to train for? Well, epochs, let's say we want to train for 2 epochs today. And we're going to do optimizer is equal to optim.atom, right? So we want to use the atom optimizer. We want to optimize what? The model.parameters. And the learning rate is 0. I'm just going to pick this for now, right? So just something reasonable and small. We have a loss function is nn.cross entropy loss. So again, all of this should feel very familiar because in the MNIST classification, we use the same things, right? We use cross entropy loss, we use the atom optimizer, so on and so forth. We're just training on images instead this time, or on a convolutional neural network instead of a linear layer like last time. Batch size is equal to, let's say, 128. And so now we need to build our data loader. So train loader is equal to data loader. And this is going to be the train data set that we defined earlier, where some batch size is equal to batch size. Our shuffle is equal to true. And num workers, let's just say, is equal to 4. And then val loader is, again, data loader. Test data set, or I guess I called it val data set. Batch size is equal to batch size. When we're evaluating, there's no need to shuffle, so we can ignore that. And then num workers is equal to 4. Right? Oh, did I not define the train data set above? Let me quickly see what I had named you. Oh, I totally forgot one important step. This is just the data set, right? This is a data set of 24,931 images, but we need to do the train test split, right? Then do that. So we can do train samples, test samples is equal to, let's say, int. We're going to do 90% of our data, so len data set for training, and then our len data set minus the same thing. So we'll do 90% for training and 10% for testing. So train samples, samples, test samples. So we have about 22,500 for training and about 2,500 for testing. So that's good. So our train data set, test data, or I guess I called it val data set, so I'll keep it the same. Val data set is equal to torch.utils.data.random split. So it's going to be a random split of our data set, and the length is equal to train samples and test samples. So this will go ahead and split our data up into train and val. So now we're good there. So let's rerun you. Should be good now. Yep. So we have our train loader and val loader. So those are our data loaders. So now we can go back here and we can continue. So now we can write our training loop. So I'm going to wrap the training loop in just a function just to keep it simple. We're going to pass into the training loop a model, a device, what are we training on, epochs, how many epochs do we want to train for, the optimizer we want to use, the loss function we want to use, the batch size we want to use, the train loader we want to use, and the val loader that we want to use. So we're going to create something called log training. It's just going to be a very simple dictionary of what epoch are we currently on, right? We just want to have something that comes out the other end of the training process that can let us visualize how the training went, right? So what epoch are we on? What was the training loss at that epoch? What was the training accuracy, right? So at the epoch, and we'll kind of talk about that in just a bit. The validation loss at the epoch and the validation accuracy at that epoch, right? So this way we can plot later an epoch versus training and validation loss and training versus validation accuracy and stuff like that. In future videos, when we start to do more, we're going to be kind of not doing this. We're going to be logging everything through weights and biases, and they're a great system through like the Accelerate platform, but today we're going to keep it as bare bones as possible. So there we go. So now we're going to do for epoch in range epochs, we can print starting epoch. Oops. Let's close that, and close that. Good. So now when we're starting this, technically epoch is going to go from 0 to 2 minus 1, so 0 to 1 in this case. We're going to epoch plus 1 just so it's actually like starting from 1, but that's fine. And then we're going to do our intermediate storage. So we're going to do training losses, training accuracies is going to be 2 empty lists, and then validation losses and validation accuracies is also going to be 2 empty lists. Now that we have that, we can now iterate. We're going to do for image label in train loader. And we talked about this last time, but typically when we're training, it's kind of nice to have a progress bar of how things are going. So TQDM is just a wrapper that goes on an iterator, and as you iterate through it, it will print out a progress bar, which is very convenient. So we have a progress bar. And what we're going to do is just like before, image label is equal to image.to device, label.to device, right? We want to put our data on the GPU to train. And actually, maybe it'll be easier if we do this. So we're going to call this random init log. So this is going to be the random initialization, a model that's randomly initialized before we train, and model is equal to train. And we're just going to pass in all the stuff that we want. We have a model, we have the device, we have the epochs, we have optimizer, we have the loss function, we have the batch size, train loader, val loader. So we're going to actually use this function. I'm going to throw a break in here and a break in here. See if there's any issues. Yep, looks like it's good. That's fine. This is the, so technically we can, at the end of this function, we're going to return the log training and the model, right? So there we go. So it doesn't throw that error. So there we go. So we have our image, we have our label, so we can print image.shape, print label. Here we go. This is our image. So we have 128 images. Each of them are 3 by 224 by 224, and we can see we have a mix of zeros and ones for dogs and cats, right? So no big deal there. We have our images prepped, and so now, just like before, we need to pass our images through the model. So we're going to do out is equal to model, and we're going to pass in image. And if we print out out.shape, well, just like expected, we had 128 images, and for each image now, we have 2 outputs, right? 2 outputs for the dogs or the cats. So we have 2 outputs there. So we have our output, and now we can compute our loss, right? Loss is just going to be the loss function, which is this one right here, the loss function, between our output and the label. So we can then print the loss, and we can see our loss is well, 0.6929, right? So that's our loss right now. And so just like before, we need to do our loss.backward and optimizer.step, right? Compute the gradients in backwards and then update our model parameters. So loss.backward, optimizer.step. Now, before we do that, we do want to do one more thing. So let's just kind of label what's going on. Compute loss. We also want to compute accuracy. So if you know accuracy, I hope you've heard of this before, but typically for classification tasks, we care about the accuracy metric, like what percentage of my predictions were predicted correctly, right? A very typical metric that we care about. Accuracy is not the end-all be-all of metrics. There's actually better ones out there, especially if you have unbalanced datasets like precision, recall, F1 score, and you are free to add in all the metrics that you care about in this training loop, right? But for now, just to keep it simple, we're going to be looking at the accuracy because our data set is actually pretty balanced. I think it's almost 50-50, so accuracy is a good metric here. So we're going to do the accuracy. And so how do we compute accuracy? So we're going to look at so let's print out real quick. What we have is two outputs, right? For every sample, we have either it's class 0 or class 1, class 0 or class 1. And so if you remember, these are the raw logits, right? The raw outputs of our model. And let's try to make our batch size a little bit smaller so it's visualizable, right? So these are the raw outputs of our model. Now, when we go to compute our loss, these will go through a softmax, and then the softmax will convert it to a probability vector, which then we do the cross-entropy stuff like we talked about and compute our actual loss. But really, our prediction is whichever one, when we do softmax, really whichever one of these numbers is larger is our prediction. So in this case, 0 is 0.0013, and 1 is 0.0110. This means this number here is larger than this number here, which means this one is the prediction for this specific sample. And then in the second one, we can see 0.004 is larger than 0.003. So it looks like this one is larger than this one. So this is the prediction for this specific sample. In the last one, you can see it's 0.01 versus 0.008. So that means this was the predicted for this specific sample. So what we need to do is the argmax, right? We need to find which row is the largest for each of them. And so we can do our predictions. Predictions is going to be torch.argmax axis, or we're going to do out axis equals -1. -1 because argmax 0 will do the argmax on every column. We want it on every row or along the last dimension. So that's -1. Sorry, misspoke. So there we go. So we can print predictions. And there you go. So in this case, we predicted 0 for everything. You would expect your model to kind of just predict one thing for everything, typically at the beginning of training, because the model hasn't learned to do anything yet. So it's just going to, all the projections are kind of maximizing one of the classes rather than the other just by accident. So there we go. We have our predictions. And what we're going to do now is, well, we have our predictions. We also have our print labels. Or I guess label, not labels. Let's fix that. So we can see this is our prediction. This is our label. So in this case, our model got 75% correct, right? Out of the 4 things, it got 3 of them correct and 1 of them incorrect. If we run it again, in this case, we can see the model is actually mostly incorrect. It got everything wrong except for the one thing, right? So we can see this happening. So we just need to compute it. We can do print predictions equal label, right? That will give us a vector of is the prediction equal to the label or not equal to the label. We can then sum them up, .sum. So this means trues are 1s, falses are 0s. So this will just add up how many samples did we get correct. We got 3 correct, we got 1 correct in this one, we got 1 correct, so on and so forth. And then we can just divide by the len predictions, right? This is now the proportion of things we got correct in that batch. So we can do accuracy is equal to that. And now that we have our accuracy, we can go ahead and store our stuff, right? So we can do training losses.append loss, and we can do training accuracies.append accuracy, right? We're going to store everything. in these lists so we can average them up later. So again, recap, iterate through your data loader. TQDM is just for a progress bar, this progress bar. Move the images and labels to your GPU, pass it through the model, compute the loss, and then store the loss, compute the accuracy, store the accuracy, and then actually update the model. Loss.backward, optimizer.step, and then lastly, optimizer.zeroGrad. Zero out all the gradients, so for the next batch. And we repeat this over and over and over again. So nothing too crazy. Now, what we talked about is it's good to keep track of how's the model doing on the training data, but every once in a while, also check how's it doing on the testing data, right? That's how we evaluate things like overfitting. So what we're going to do is just copy all of this because our training loop will look identical to our testing loop. So there we go. And we're going to do here, instead of train loader, it's going to be val loader, right? And we're going to load our images. We're going to do a with torch.inference mode, right? Because we don't need, when we're inferencing our model, there's no need to do any kind of gradient calculations or anything like that. So we're just evaluating the model. So there we go. We will compute the loss. That's going to be here for this specific one, and we're going to store it inside the validation accuracies this time, or validation losses this time. Similarly, we'll compute the accuracy. We're going to store that inside the validation accuracies. And obviously there's none of this. There's no optimizing happening, so we can delete all that. Last thing we need to do, and again, we haven't talked too much about this yet, so we're going to dig into this later, but we need to include a model.train. This puts the model in training mode, and then model.eval. This puts it in evaluation mode. And what this is doing is, for anyone who knows, already knows, right? We have dropout. So we have some things here called dropout. We haven't talked about dropout yet. It's a powerful regularization technique that we'll talk about in the future, I think next time. But dropout is basically something that will do something during training. It's doing something during training, but we don't want it to do it during evaluation. That's basically the idea here. It's going to do something during training, but we don't want it to do during evaluation. So model.train turns this on, model.eval turns it off. And that's basically the big idea. So we're going to be just doing model.train, model.eval, and we're good to go, right? These are our two training loops, and we'll get rid of the breaks in just a bit. Last thing is we need to now compute how did the model do on this epoch, right? How's the model doing? So I think I have everything lined up correctly. So yes, yeah, okay, good. So we're going to do training loss mean is going to be np.mean, training losses. And actually, I made one spelling mistake here. Append. And actually, one other thing we need to do is not just loss, but loss.item. If you remember, if you print out the loss, it'll print out a bunch of information, like the gradient information and all of that. We don't need all this gradient information. We just want the number itself, like what is the accuracy. So there we go. You should have seen that in the very first tutorial as well. So we have that, np.mean, training losses, and we can just copy paste this 4 times for the 4 different lists that we had. Oops. There we go, and there we go. Right, so training loss mean, training acc mean will be the training accuracies. Our val loss mean will be our validation losses, and our val acc mean will be the validation accuracies, right? So we're just going to average up how it did on this specific epoch. And then we can go ahead and store them. Log training epoch dot append epoch, and then log, actually I'll just go ahead and copy paste this because there's nothing really anything happening here. I just don't want to type all of it. So we're just going to take you, right there, and put you right there. Right, so we're just going to go ahead and store everything. training loss mean. I guess I call these valid loss mean, valid ACK mean. There we go. Right, this is gonna go ahead and store everything. So if we run this, looks like I missed a extra parentheses right here and right here. And torch.inference mode, there should be a colon right there. And there we go. So this, it didn't train anything, it was just one iteration. But we can then look at our log training and see for the, random init log, right, nothing has been stored yet, so that's fine. Neat. So we can go ahead and let this run. Let's get rid of the breaks. So again, we are training this for 2 epochs. And what we want is, let's say, do a batch size of 128. So put that back the way it was. And hopefully this works with no issue. So we can see it's running. We'll see in just a second if there's any bugs in it. I don't think there is, but they always seem to sneak up on you. So here we go. Training, training, training. All right, now it's doing the evaluation loop, and there we go. We can see on the first epoch, we got 64% training accuracy, 72% validation accuracy. Now you might be asking, how is it that the validation is doing better than the training? This typically happens due to things like regularization and dropout and all that, and we'll talk about all that later. But we can see with 2 epochs of training, we got 81% validation accuracy, which is actually pretty good, right? That's actually pretty good. 80% accuracy on like a dogs versus cats, not bad, right? Not bad at all. But this should give you a quick idea of what we did, right? So this training loop will kind of come back a couple of different times through the next few tutorials, but the idea is always the same, right? So hopefully this made sense. I would just step through this once on your own, kind of look at the shapes, see how things are going on, but it should be pretty self-explanatory. So now that we have this done, right, now our question is, what happens if we do the same thing, but instead we load some pre-train weights, right? Pre-train weights. So what we're going to do is our model is now, instead of just being AlexNet, we're going to do torch.hub.load, and they call it, actually let me just copy this. We're going to just load the pre-trained model. So let's comment you out. So this is how you can load pre-trained models from PyTorch, or you can use Hugging Face, whatever you want. It doesn't really make a difference. So we loaded our model, and exact same model that we saw before, nothing brand new, and it still has the 1000 output classes. The difference is this model has been pre-initialized. It is pre-trained on the ImageNet task, so it can classify one of those 1000 things. And so what we're going to do is we're going to, just like before, go ahead and swap the last layer out so it has 2 outputs rather than 1000, and everything else will stay the same. We're going to again do epoch. Epochs is 2. Our optimizer is equal to optim.atom, model.parameters, learning rate is 0.0001. We're going to do a loss function again of nn.crossentropy loss, and our batch size again will be equal to 128. Right? We already had our train loader and val loader from before, so we can just go ahead and copy you over, and we can do, this is called pre-init log, right, for the new initialization. And in this case, I think everything else is correct. So I think we're good. Let's see. So this time we're training our model, but our model has already been pre-initialized with those ImageNet weights, right? So we're using these pre-trained weights. So we're going to go ahead and run them. So one thing I do want to mention, I guess I failed to mention this, is this model here is fully pre-trained, right? Fully pre-trained, which means it can do the task. When we swap a layer out like this, classifier 6 is nn.linear, swap it out, this new layer is randomly initialized and needs to be retrained, which makes sense, right? We're doing a new classification task that wasn't the original ImageNet classification. So if we're doing a new classification task, we need to also retrain this layer. The thing is that when we train this model, we're actually training the entire model like normal, just like we did before, but only the last layer is randomly initialized. And that's the only thing to really keep in mind. And you can see when we do the training, we get 97% accuracy in 2 epochs of training. So you can think about this in terms of compute budget, right? Compute budgets is always, as a researcher, right, we're always chasing after more compute because you have to write all the proposals and stuff like that, and you need to like get some budget and an allocation and whatever it may be. The problem is that if your model takes very, very long to train, then it just requires more compute. You need to request for more resources. Everything takes longer. By starting with a pre-trained model, you can get very good results with very little effort, right? That's the big idea here. If you want to train, we could get this model to be better. We'd probably have to train it for longer. I don't actually think this model will reach 97%. I think this one will reach maybe like 85% or maybe 90% or something like that if trained for long enough. But that's fine, right? This is clear evidence that, hey, starting from pre-trained weights is definitely better. And we can see those benefits right here. So this is a pre-trained model. Now, let's go back here, right? We talked about this a little bit. We first pre-train our model. So this is AlexNet. And then for the new thing we want to do, comparing the leaves, we will start with the pre-trained model and swap out the classifier layer. And swapping out the classifier layer is done here. That's this line right here. The question becomes this. When we train this model, we're actually training everything. All of these parameters in the new classifier and the pre-trained feature extractor, they are all learnable. Everything is learnable. Now, if you have enough data, this is probably fine, right? In our case, this is actually fine in our dogs versus cats. But if you don't have very much data at all, if you only had 100 samples, even starting with pre-trained weights, you'll likely overfit. So a typical thing to do is to say, okay, I trust that this feature extractor here is already extracting useful features from our data. Which means why not load the pre-trained weights here and then lock it down. Lock it down so these cannot change and only this is trainable. And so the way to think about this again is if we print out our model, here's our model. All of this is currently learnable, right? If we iterated through the parameters, everything has a requires grad equals true flag. Everything is learnable. What if we lock it down and only train the classifier, right? Or what if we lock down everything and most of the classifier and only train the last layer, right? So one way to think about this is the more data you have, the more layers you can allow to train, typically starting from the end. So if you have a lot of data, then you can go ahead and train the entire classifier. If you have very, very little data, to avoid overfitting, you might just train the last layer or the last two layers or something like that. Right? So again, this isn't intuition that I can just give you. It's something that comes with experimentation. You have to try on your own problem, see how it's working, things like that. But what I want to show you then is, okay, how do we lock it down? So like we saw before, we can do for name param in model.named parameters. Print, let's do if bias in name print param. Okay, this again applies to everything. All the learnable parameters. I'm just printing the bias because it's short and sweet, so I can, I don't have to scroll all the way down. It's very simple. And notice this requires grad equals true flag. This means this set of parameters, right? This bias is learnable. It is capable of doing gradient update when we pass it to the optim.atom model.parameters. Atom will update these weights, and what we want to do is turn it off. So which one do we want to turn it off for? Well, let's look at all of our names again. Again, for name param in model.named parameters. Print the name. Right, here is all of our learnable parameters, the weights and biases. And we can typically do this off the name. You can just create a kind of a rule and saying, hey, if I only want to train the classifier, then turn off weight updates on anything with the name feature in it. Like if feature is in the name, then turn it off. Or if I only want to train the last layer, right? So only the last classifier, then if classifier.6 is in the name, then let's go ahead and train it. And if classifier.6 is not in the name, then we have to turn it off, right? So you can make this as complicated as you want it to be, but this is just a general idea. So we're going to do for name param in actually, let's go ahead and copy this little chunk here. So all of this stays the same, just like before, right? We have our model, nothing crazy. And what we're going to do now is for name param in model.named parameters, if classifier.6 not in name, right? So anything that's not class, then we can print out the name. Well, here we go. These are all, notice how we're excluding, right, classifier 6, so it ends at 4. And we don't really care about the name. What we really care about is the param. Now let's just break it here. This is, again, why I don't print them all out, but this is all the parameters of our first convolution. Notice it has the require grad equals true flag enabled. So we're going to go ahead and shut it down, right? We're going to do a quick param dot requires grad as false, right? An in-place replacement. And so now we can do for name param in model dot named parameters print param and break. Now you should see we still have the same parameters, but notice there's no longer a requires grad equals true flag here, which means this parameter is no longer gradient updatable, which is nice, right? That kind of solves that problem. So we've effectively locked down the model, except for this last layer. Now the other benefit of locking down a model, except for the portion you want to train, is not only does it take less compute time, it will also take less memory, right? You have less states to keep stored in GPU memory. Everything becomes simpler, and this is a very typical method of doing it. So now that we have that, everything else is the same as before, so we can go ahead and just copy it. So we're going to grab all of you, and again, we're just going to train for 2 epochs, just like before. Nothing else changes, except we are just training this last parameter now. This is again a, these are very typical techniques we use in neural network training. It's very rare unless you've come up with a new novel idea to pre-train a model on a large data set from scratch, typically because the access to the resources necessary to do that kind of training is just not available to most people, right? Only large companies and institutions will have giant GPU clusters just available to them to train these types of models. But luckily, they make lots of these types of models accessible to us, so we can train them ourselves. So one thing to keep in mind, notice, obviously this is just from our case, but we got 96.5% accuracy on the pre-trained weights where we trained everything, and then we got 96.6% accuracy this time, right? So ballpark about the same. We only trained the very last layer of the model, yet we got very similar results, which is always promising to see. But yeah, that basically rounds up the idea, right? The big idea here is pre-trained models allow us to transfer knowledge, right? So I haven't used this word too much yet, but you can think about that these feature extraction, this entire feature extraction phase that this neural network goes through, this is basically a bank of knowledge, right? It's numerically encoded information that the model uses to do the classification tasks that we care about. So our hypothesis is that, well, if the model already has a bank of knowledge that more or less understands the domain of images, why not just transfer that knowledge, right? Transfer that bank of information to a new application, right? That's the main idea here. The main perks of this is, first of all, it's feasible, right? I can grab a model and fine-tune it within a reasonable amount of time. Pre-training can take weeks or months, depending on the types of data sets they're trained on massive clusters. There might be thousands of GPUs involved, lots of money goes into it. There's typically entire teams monitoring those types of large compute trains because just to verify that things are going well. That's not accessible for me, the single researcher, or you kind of trying to work on these types of projects. So yeah, it becomes accessible is the cool part, and the best part is in this field, all the pre-trained weights are typically published, so you can just go access them and use them. This allows us to apply models that are trained on big generic datasets. Like datasets like ImageNet are big generic datasets that aren't really good for anything of use except for really pre-training. I mean, obviously image classification is an important task, and ImageNet is one of those datasets that we can use to perform image classification, but in most research today, you're working on something interesting like classifying leaves, right? So if you're trying to classify leaves on a niche task, you can still use these models. There's less concern for overfitting, right? Especially if you're just training a small part of your model, then it's unlikely that your model will just overfit or memorize the data, even if you have very small data sets, which is really nice to see. And less compute. Again, like I mentioned, right, you can actually train these models. So neural networks, again, pre-trained models is basically why neural networks are so popular. They can be transferred to any kind of modality that you want. We did image classification here, but this whole principle applies for text or genomics or graphs or really any data. It doesn't matter. As long as the original pre-trained model is trained on a massive amount of some type of data, then you can effectively transfer learn to a new to a new kind of problem in that modality. So either way, if you have any feedback, if you have any questions, drop it down below. Let me know how this is going. If I could be clearer about something, that would be great for my own learning. But I'll call it here. Next time we will be actually implementing AlexNet, so you can see how the model comes together. Everything else we're just going to reuse. So I would recommend make sure you understand the training loop. Make sure you understand some of the stuff that we did through here, because we'll be copy pasting some of it in the next one. So I will see you then.